brought down by an unseen fire. A catastrophe that transforms aviation. The shocking discovery that seats are a death trap. Scientists investigate the mystery of some of the world's worst plane crashes and search for the breakthrough technology that's made your next flight a whole lot safer. January 25th, 1990, as fog engulfs JFK, planes stack up overhead. The tower routes Avianca Flight 052 for final approach. At 600 feet, the pilot hits a blast of turbulence and aborts the landing.
We just missed a misfortune. We're maintaining 2015.
Then, the pilot relays bigger news.
And now we're running out of fuel.
The 707 is now running on fumes.
Avianca 052, you have enough fuel to make it to the airport? Avianca 052, New York. Avianca 052, radar contact lost.
Flight 052 crash lands in Cove Neck, Long Island. No fuel, so no fireball. It belly flops on a slope, splits in two, then shudders to a stop. 85 survive, 73 die. When Barry Trotter and a team from the NTSB examine the wreckage, they make a chilling discovery. More should have survived.
The majority of them died because the seats failed. So the passengers still strapped to their seats were moving forward and bumping and piling up against the other passengers ahead of them.
When you think about the fact that the fuselage stayed together and protected the people in that way, it's the seats that didn't protect the people. Their seatbelts stayed intact, and the rescuers said that all the seatbelts were attached, but with the seat not staying attached to the airplane, you lose all benefit, any protection of the restraint system, because you go flying with your seat.
It's not the first time seats failed so badly. 8 years before, horror in the nation's capital. Air Florida 90 came down in the Potomac River.
Investigators have found the victims of the Air Florida disaster were not killed by the crash impact of the plane with the bridge or river. Instead, they died when almost all the seats broke loose.
By the time of the Cove Neck crash in 1990, aviation has gone through a digital revolution. But back in the cabin, passengers are still living in the 1950s. Rules dating back to 1952 state that seats must withstand a force 9 times stronger than gravity. Here's how they tested a seat. Load it with a block of wood and pull it in all directions at 9 Gs.
The problem with that test was that it was a static test. That means, in engineering terms, it was a slowly applied load. Of course, a crash is a very rapidly applied load.
Throughout the 70s, engineers conduct all sorts of dynamic tests, but only on the airframe, not the seats. Not until 1981 does the FAA finally open a facility to dynamically test seats.
One of our most spectacular videos that illustrates the problems with the 9G seats, we called it Flying Freddy.
Freddy reveals the fatal flaws. The legs sit rigid in a lightweight track. On impact, the track buckles, and mayhem. The legs are cast from brittle steel. They can't absorb the kinetic energy thrown at them during the crash. "9G was out. Seats had to withstand a stronger force. But how strong?
There was a lot of research that went into determining just what G level was being experienced by the occupants of survivable airplane crashes. And this is from dropping fuselages and controlled impact demonstrations.
At NASA's drop test facility in Langley, tests reveal that both passengers and aircraft floors can survive impacts up to 16 Gs. The FAA sets a new gravity goal, but faces an even tougher challenge. Design a seat that can run down this track at 44 feet per second and survive a sudden halt equal to a 16G impact.
The seat structures needed to be strong, but also light. So that ended up being a catch-22. If you made it stronger by making it heavier, because it was a dynamic test, now that weight worked against you. Seat manufacturers would bring in prototypes. We'd put them on our test sled, and invariably, they would simply break loose and go flying off the sled.
While tests continue, the world's fleet is still flying with 9G seats, the standard set in 1952. Finally, in 1986, the breakthrough. And this is how they did it. First, they fit a flexible stud to the end of the seat leg. When the track buckles, the foot swivels instead of snapping out. Second, they cast the legs in a C shape. In a crash, the back legs straighten and the front legs compress. As the legs crumple, they absorb most of the kinetic energy of the impact.
When that seat finally stayed on at 16 Gs, everybody was pretty enthused. There was some jumping up and down and hollering going on.
In 1988, manufacturers fit 16G seats on new planes. But it was judged too expensive to retrofit the entire existing U.S. fleet. 1 year later, a Boeing 737 crashes on a freeway in England.
The broken Boeing, 4 months off the production line, so profoundly distorted that in the cold light of day, it was hard to imagine that anyone could have escaped alive.
47 die, but experts believe that many of the 74 survivors owe their lives to the new 16G seats.
It was the first crash that involved seats that had been tested here at CAMI and had passed our 16G requirement.
When Avianca 052 crashed at Cove Neck 12 months later, it still carried the old seats. Experts believe that lives could have been saved if the plane had been fitted with 16G seats. Not until October 2009 will they become mandatory on all aircraft. Los Angeles has always had some of the busiest skies in the country. In 2008, almost 60 million people flew in and out of LA in one single month. Busy skies, but closely watched. Over an area of 7,000 square miles, 25 airports, employing nearly 300 air traffic controllers. August 31st, 1986. A clear day with visibility up to 14 miles. At 11:46 a.m., the LAX tower clears Aero Mexico 498 for descent. On board, 58 passengers and 6 crew. 6 minutes later, the DC-9 disappears from the radar screen. A photographer captures the moment it drops from the sky.
Talking about tons, literally tons of aluminum and parts coming down in a very uncontrolled fashion.
The DC-9 crashes over the sprawling suburb of Cerritos.
There's smoke, there's fire everywhere. It creates an enormous destructive path. It's carnage.
Rescue teams quickly make a grim discovery. The wreckage is from 2 aircraft. In a schoolyard, they find the fuselage of a twin-seater Piper. All 67 people on the planes are killed, 15 more on the ground. How did two aircraft collide on a clear day in such closely watched skies? Two planes have collided in mid-air over Los Angeles. Investigators must probe why. They check the flight records and discover the Piper left Torrance Airport 12 minutes before the crash. It ascends to the wrong altitude and enters the LAX terminal control area, flying straight into the path of Aero Mexico 498.
The air traffic controller didn't know they were there. The Aero Mexico crew clearly didn't know they were there, and the Piper, in all likelihood, believed that they were outside of airspace that would present them any danger. In fact, they weren't, and the collision occurred.
All pilots learn the first rule of aircraft separation. It's called see and avoid, a method as crude as it sounds. In tests, it works barely half the time. Investigator and ex-pilot John Cox knows why.
It is very difficult to see a small aircraft, particularly when they pose a threat to you, because they're oftentimes virtually head-on, so that they don't present a large profile, so it's very hard to see them.
Two planes are flying over Arizona on a deliberate collision course.
Closing with the other aircraft right now. He's about 17 miles ahead of us, and we're closing at about 400 knots, which is about 450 miles an hour.
That means they're traveling at a combined speed of 900 miles an hour. They'll meet in seconds. Only now does the co-pilot spot the other aircraft. They've seen and have split seconds to avoid.
He's off to the left there.
If the pilots hadn't been looking for the other plane, they'd probably have collided.
Human eye isn't very good at picking out little specks on the horizon. And if you're actually going to run into another aircraft, that little speck is not moving around at all. So it's extremely difficult to see, even on a clear day.
The Massachusetts Institute of Technology has studied the effectiveness of see and avoid. The engineer in charge of the investigation is John Andrews.
In the case of the Cerritos accident, the aircraft were closing at almost 300 knots. And what that means is that in order to see the aircraft in time to avoid, you would have to see it at about a distance of 1 mile. That's 13 seconds approximately before the collision. At a distance of 1 mile, the Piper aircraft, the smaller aircraft, was the same size as a US 1-cent coin at 40 feet.
The drawbacks of see and avoid became clear in the 1950s as planes flew faster. In 1956, a mid-air collision over the Grand Canyon kills 128. At the time, it was the world's deadliest air crash. Research begins on the holy grail of air safety, a collision avoidance system. But work stops after 6 months. The technology just doesn't exist. By the late 1970s, however, avionics had moved on. Aircraft now carry a device called a transponder to avoid mid-air collisions. Using transponder beacons, air traffic control can track a plane's location, altitude, and call sign via ground receivers. But the advance is not foolproof. Pilots must rely on air traffic controllers for a warning. 1978. On approach to San Diego, a 727 collides with a single-engine Cessna. 137 die. Spurred by the tragedy, John Andrews' team at MIT worked to develop a traffic collision avoidance system, or TCAS. The goal, to develop a cockpit warning system which will alert pilots to nearby planes.
Hundreds and hundreds of hours of testing had to be done to bring the system to the point where we could actually say if this were installed, it would work.
Andrews tests his prototype by rerunning the fatal flight at San Diego.
We equipped a 727 and a small aircraft, exactly the same type aircraft that collided, and flew them with TCAS equipment on board to test and see whether or not the electronic part of the system was good enough to have prevented that accident. Our conclusion was that we could do it with existing transponders.
TCAS signals all aircraft transponders within a range of 40 miles. Transponders on nearby planes respond with speed, altitude, and call sign. If planes are heading on a collision path, TCAS warns one to ascend and the other to descend. Finally, the solution. But at $60,000 each, it's an expensive fix.
For a while, there was obviously reluctance to spend all the money it would require to equip commercial aircraft with TCAS. It was considered to be a fairly expensive piece of avionics.
Then, the mid-air collision over Cerritos, a virtual rerun of the San Diego crash.
And Cerritos was the key event that pushed the system from the laboratory and from the experimental flying into actual daily operational use.
After Cerritos, the FAA makes TCAS mandatory on all large U.S. aircraft. In 1993, it was required on all planes carrying more than 30 passengers.
Descend, descend. Traffic, traffic.
Today, every plane entering U.S. airspace is required to have it.
Aircraft that's plus 100.
TCAS has literally saved numbers of airliners, including one that I was flying. We would have probably struck a small airplane over Central Florida had we not had TCAS warning.
June 1st, 1999. American Airlines 1420 from Dallas-Fort Worth makes its final approach into Little Rock. As they head toward runway 4R, they fly into a tempest.
It was a very stormy night, and the airplane was late, very late.
They landed on a rain-flooded runway in very high wind conditions.
He had to land on the high side of the speed threshold because of all the events going on around him.
And went off the side back to the center.
And he went off the end going quite fast.
146 lives hang in the balance. Little Rock, Arkansas. A plane crashes in a severe thunderstorm.
We just kept on going and we slid off. And all I remember is the stewardess screaming, brace.
We started to turn the plane just started sliding.
I just held on and prayed that, that I would see my parents.
Most of the 146 on board survive. The pilot and 10 passengers die. The survivors have a lucky escape. The aircraft stopped just short of the Arkansas River. Investigators piece together the final moments. The plane left the runway at high speed, smashed into a lighting gantry, broke into 3 sections, and burst into flames. They conclude that the pilot shouldn't have landed during a level 6 thunderstorm, the most severe. The crash is classified as a runway overrun.
Most of them never make the paper. Most of them are non-events other than the airplane went off and gets stuck in the mud. You see more serious ones also every year.
Runway overruns happen alarmingly often. In the U.S. alone, one occurs about every 10 days. They happen on both takeoffs and landings and cause 1/4 of all aviation deaths.
Southwest Airlines Flight 1455 skids off the runway in Burbank, California, stopping just short of a gas station.
Federal authorities agree there ought to be something more than 82 feet between a speeding 737 and a crowded neighborhood.
The FAA recommends that runways add a 1,000-foot safety runoff. But most U.S. airports were built before the jet age for prop planes that need less room to take off and land. Many older airports lack room to expand. Among them, one of America's oldest airports, Little Rock. The safety area for runway 4R was just 450 feet, less than half the room recommended by the FAA. New York's JFK International Airport is even more cramped. hemmed in on 3 sides by water. On February 28, 1984, a DC-10 overshoots runway 4 left and ditches in Jamaica Bay. Miraculously, all 177 passengers and crew survive. The manager of aeronautical operations at JFK is Pam Phillips.
The question was raised. We had this overrun. What can we do? What can we do to further the research associated with looking at something new, looking at something fresh, looking at something different?
What's needed is a way to stop planes quickly and safely when they overshoot. For an answer, the FAA turned to the guys who can stop planes fast. Arresting systems can stop military jets traveling at speeds up to 170 miles per hour in just 600 feet. But planes like these are built to absorb the intense shock. If a commercial aircraft is abruptly stopped, most of its kinetic energy rebounds on impact, damaging both plane and occupants. What is needed is some sort of material that can absorb most of the energy of impact and bring the plane to a halt in a controlled manner. The FAA become particularly interested in something called phenolic foam. It's light, rigid, and crushable.
Not the fluffy pink stuff that you think of when you think of household insulation, but it's a firm foam. If you've ever seen the things that florists use to poke flowers into.
But this foam had a drawback.
If there were an accident, there is potential for a fuel spill, and this material could soak up jet fuel and prolong a fire.
It was a setback, but they didn't give up on foam. They turned to foamcrete, a specialist concrete mixed with liquid soap, which in turn traps air bubbles in the mixture. It's tough, but much lighter than standard concrete because it's full of air and it doesn't burn.
We really thought that we were onto something with this new cellular material. In essence, it's a strong material in some respects and a very weak material in other respects.
Strong enough to withstand 115-mile-an-hour jet blasts and the extreme temperature range at many U.S. airports. Computer trials suggest it's also weak enough to give under the weight of an airplane. As foamcrete crushes, it absorbs the forward energy of the undercarriage and slows the plane gradually. It's like trying to ride a bike through sand. It works in theory, but how about on the runway?
The big day was back in May of 1996 when we had a 380-foot long, 40-foot wide bed built. We actually had borrowed an FAA Boeing 727.
The jet is traveling at 50 miles an hour.
We actually had a couple of our employees on the plane.
The 727 hits the foamcrete at high speed. The landing gear absorbs the shock. And 10 tons glide to a halt.
And what's amazing about it was that the aircraft stopped within 16 feet of what our computer model had predicted. Everybody was just ecstatic about it, and having it stop like it was supposed to, that's all you could ask for.
They dub it Engineered Material Arresting System, EMAS. In months, the first EMAS bed is laid at the end of JFK's runway 4 right. But will it work in a real emergency? To stop runway overruns, JFK installs a bed of foamcrete. The bed goes unused for almost 3 years. Then, on May 8th, 1999, Pam Phillips gets a call.
It was Mother's Day of 1999. It was a day much like this. It was rainy, it was gray, and I will never forget getting the phone call.
A Saab commuter jet landed long and ran straight into the EMAS bed.
Came out here to JFK and was everybody okay? No injuries and no damage to the aircraft. Everything that we expected through all of the testing and research validated itself with that arrestment.
4 years later, the EMAS bed stops an MD-11 cargo plane. And in 2005, EMAS passes its biggest test so far, pulling up a 300-ton 747 racing at 80 miles per hour. To date, foamcrete has been installed at 30 airports across the country, including runway 4 right at Little Rock.
Quite frankly, I think that EMAS probably is the most revolutionary safety device that's been put into civilian aviation certainly in my 20-plus year career. Absolutely.
September 2nd, 1998. Swiss Air 111, en route to Geneva from New York, heads north over Canada. It's flying at 33,000 feet with 229 people on board. Air traffic controller Bill Pickrell is coming to the end of his shift.
About 10:15 local time, we were advised that there was a Swiss Air flight that was diverting into Halifax for a precautionary landing.
Swiss Air 111 Heavy is declaring stand after smoke in the cockpit. Request immediate return.
A PAN means something is urgent, but it's not a full-scale emergency.
They didn't think it was serious, but this was an aircraft that was about to go across the North Atlantic.
Before landing, they have to take precautions.
We must dump some fuel. Maybe do that in this area during descent.
Are you able to take a turn back to the south, or do you want to stay closer to the airport?
Stand by short.
No sense of urgency in the pilots' voices. There was no way of knowing that the situation on the aircraft was changing.
We are between 12 and 5,000 feet. We are declaring emergency now at time 0124.
Swiss Air 111, check you're cleared to start fuel dump.
As the pilot tries to speak, he's abruptly cut off. With all contact lost, Bill Pickrell can only watch the radar as the plane flies erratically out to sea and then disappears.
What followed was about a little more than 5 minutes, almost 6 minutes of probably the most helpless feeling you can imagine. I feared the worst. I expected that he was in the water.
Swiss Air 111 has plummeted into the Atlantic Ocean 6 miles off the coast of Nova Scotia.
Heard a loud, it wasn't even an explosion, it was almost like an air wave sort of hit the top of the house and the windows shook.
Local people rush to help. Among those watching the news is Larry Vance of the Canadian Transportation Safety Board.
Came on newsflash over the television, and I said to my wife, "Ooh, this sounds like one I might be involved in," so I waited for the phone call.
The investigation begins immediately. The team is based at a fishing village, Peggy's Cove.
The mood at Peggy's Cove was quite somber. I mean, you got 200 bodies out in the ocean. Well, for us in the safety board, it was the biggest investigation that we ever launched, the biggest one we ever participated in.
The black boxes are quickly found, but they solve nothing. For some reason, the tapes cut out 6 minutes before the crash. The key to the mystery lies on the seabed. When the plane hit the ocean, it broke into millions of fragments. Each has to be found, raised, and inspected. But the wreckage lies at a depth of 180 feet, and it will take a massive salvage operation to retrieve it. To solve the mystery of Swiss Air 111, investigators must salvage millions of pieces of wreckage. It's an immense operation, costing over $30 million. After 15 months, they recover 98% of the plane. In a hangar, each piece is carefully washed, sorted, and examined. But the first clue is the pilot's own words.
Smoke in the cockpit, request immediate return.
Much of the wreckage is blackened. There is molten plastic in the cockpit. The controls are burnt and the wiring destroyed. Evidence of a catastrophic fire, and the likely reason why the data recorders stopped working 6 minutes before the crash. To pinpoint the source of the fire, the team reassembles the front 30 feet of the plane.
Well, we reconstructed the wreckage on the frame to understand the extent of the fire damage. We were trying to delineate where it started and where it ended.
The reconstruction reveals that the fire began above the cockpit, in an area known as the attic, invisible to the crew.
A hidden fire in an aircraft is one of the more dangerous things that you can have happen to you as a pilot or as a passenger. If you have a fire in an aircraft that you can't detect, that fire will, unless for some reason it self-extinguishes, the fire will spread through the aircraft and eventually it will bring the aircraft down.
If the fire started in the attic, then the most likely cause is electrical. 150 miles of wiring runs through the plane. Thousands of them lie in the attic. After 4 years of careful scrutiny, they find the source of the ignition. A piece of wire from the in-flight entertainment system. Investigators believe that 2 wires chafed on a metal bracket, wearing away the insulation. An electric arc from the exposed copper then sparks the fire. The blaze destroys vital instrument cables. Out of control, the plane plummets into the sea. But the only material near the wiring is the plane's insulation blanket, and it's not supposed to burn. So how did the fire spread? Investigators zero in on the flame-proof material that covers the insulation. It's called metallized mylar. The industry standard tests, which are demonstrated here, show that when exposed to a flame, mylar shrinks but does not ignite. But there is a question mark about the test itself. There had been reports that despite the tests, metallized mylar was, in fact, flammable. The FAA devises a tougher test that more accurately replicates a plane on fire. It's called the Radiant Panel Heat Test. The results are shocking. Mylar burns.
We were very much concerned, and we were concerned that there might be other incidents, and because of that, the FAA issued an airworthiness directive that would require the actual removal of metallized mylar from over 700 airplanes.
Metallized mylar is yanked from all aircraft. Scientists look for a replacement that won't burn. They decide on a material called Kapton, a variation on the insulation used on electric wiring.
Chemically, it has a makeup that produces a char when it is exposed to heat. This char is a factor in its fire resistance because a char prevents the material from igniting and burning.
Kapton passes both the Bunsen burner test and the radiant panel heat test. It does not burn in either. But to be sure, the FAA subjects it to the ultimate test, 15 seconds in an 1800-degree flame. At these temperatures, the plane itself would melt, but the Kapton is only charred.
The most important thing is that once the flame was removed, it did not propagate a fire and it self-extinguished immediately.
Across America, this remarkable material, which lines the entire fuselage of a plane, will ensure that the horror of a hidden fire will never be repeated. Los Angeles International Airport, February 2nd, 1991, 5:58 p.m., the busiest time of the day in the control tower. US Air 1493 is en route from Syracuse, New York. As it makes its final approach, the pilot confirms clearance to land with air traffic control.
Yes, sir, 1493 for the left side, 24 left.
Yes, sir, 1493 for the land runway 24 left.
The pilot's visibility is severely impaired. He is landing into the setting sun. But then he sees something on the runway.
That's a hill.
When emergency crews arrive on the scene, they make a chilling discovery.
Firefighters first on the scene didn't even know there was a second plane involved for at least 4 minutes.
Then observed the propeller, realized that the propeller didn't belong to a 737, and then went back out on the airport to look for the rest of that airplane.
The propeller belongs to a SkyWest turboprop, which was sitting on runway 24 left, awaiting clearance for takeoff. All 12 people on the turboprop are killed. 22 die on the 737. Within hours, crash investigator John Cox is on the scene.
What we saw when we went out there was a very badly damaged 737, both due to the impact as well as the ensuing fire, and the crumpled Embraer up underneath the Boeing. It was a very tough place to work.
Just how could two planes collide on the runway? Two planes have collided on a runway at LAX. An investigation by the National Transportation Safety Board quickly finds out why.
The fault was found to be the air traffic controller working the tower at Los Angeles. Forgot that she had instructed the SkyWest airplane onto the runway. She lost awareness of where that airplane was.
1493 for land runway 24 left.
Certain times of the day, the air traffic controller probably feels like their head is in a vice. On busy airports with airplanes coming and going, it's very easy for controllers to lose track of exactly where an airplane is.
It's the controller's job to keep a safe distance between aircraft. The most dangerous place is where planes are moving fast out on the runway.
When there's an airplane on approach or on takeoff for that runway, that is sacred ground. And you cannot bring any other vehicle into that sacred ground.
This is the result when that ground is violated. March 1977, at Tenerife in the Canary Islands, two Boeing 747s collide at high speed on the same runway. 583 die in the world's worst aviation disaster. Heavy fog led to miscommunication between pilots and controllers, human error, and technology failed to detect it. Controlling air traffic is one of the world's toughest jobs.
1500, cross 4 left, straight down the runway, ground point 9.
Cross Delta, you can go left Bravo, because I'll give way. Cross American and Austrian and Qatari.
The JetBlue owner is waiting for you. Cross 4 left.
Controllers at major airports, like New York's JFK, regularly handle up to 100 flights an hour. Since the 1950s, most airports have been equipped with radar systems to monitor traffic. Ground radar sends out radio waves which are reflected back from aircraft. The plane's position can then be tracked by the tower. But controllers must manually match every radar blip with each plane's call sign. Hard work at rush hour. Worse, the radar signals can be deflected by heavy rain, snow, and fog.
Surface radar as we have it today does have some limitations. There are blackout spots that it doesn't return very well. There are false signals sometimes.
But a team at Syracuse, New York has developed a life-saving solution. They call it Airport Surface Detection Equipment, or ASDX. As a plane moves across the airport, its transponder sends out data such as the flight's call sign. Sensors along runways receive the signals while constantly tracking the aircraft's movement. No blind spots, and the sensors work in all weathers. The data is relayed back to the tower and displayed on the ASDX monitor. Over a map of the airport, It continuously displays all traffic movement. Now, controllers can instantly prevent planes colliding. And they don't need to manually identify planes. This system automatically recognizes and displays each aircraft's call sign. As planes move along the runway, a series of green lines warns controllers to block other traffic. When the danger passes, the controllers can safely direct traffic across that runway. ASDX was recently installed at JFK, and today they may need it more than ever. A 757 is making an emergency landing with reports of smoke in the cockpit.
You can contact ground on 121.9. He wants the vehicles to inspect the aircraft.
Okay. Worst case, they're going to blow away chutes and also got people all over the place. So we're going to want to make sure we don't have anybody. We'll try to keep all airplanes off of Alpha and Bravo.
If passengers need to evacuate the plane, controllers may have to close runways.
Yeah, I know. Yeah, I know. That's
If they close a runway, the monitor displays a warning. If a plane approaches the runway, ASDX will sound a conflict alert.
Warning, runway 22 left. Go around.
In certain scenarios, it can provide as much as 15 seconds warning. In others, it can be less than 10 seconds. But what we have to understand is that even if it's less than 10 seconds, that is the difference between life and death.
ASDX will greatly reduce the risk of a tragedy like U.S. Air Flight 1493 happening again. It has now been installed at 17 airports across the nation, including LAX. None have suffered a runway collision. Today, Boeing are developing the next step in collision warning systems in the cockpit.
Here comes the 777 checks.
These pilots are testing the system on a simulated journey across fog-bound San Francisco International.
This guy's going to take off in front of us.
They turn onto runway 19 left and wait for clearance to take off.
Tower, Boeing 001. I'm waiting for takeoff clearance. Still waiting for my takeoff clearance, and I don't have it yet. But right here, there's an airplane right behind me getting ready to land. He's 2.4 miles out.
Tower, Boeing 1, we show traffic landing on runway 19 left. Do you want us to depart, sir? We've lost comm with the tower, Captain.
That's much too close for me.
Boeing 1 transmitting in the blind. We show traffic on our tail. We're exiting the runway. It's within 1 mile, Captain. Miles, 0.5 miles, closing. Well, that's close.
Without the cockpit warning, disaster. Today, decades of innovations safeguard flyers against collisions on the ground and in the air, hidden fires, and runway overruns. One leg of any flight is still risky, the drive to the airport.